This video is an explanation of projections on a horizontal plane in applied maths. Oh look, a catapult. Is that a snail shell? On the left are the equations of motion. These are used in most areas of applied maths. The letters' meanings are shown on the right, and as it says below, these can be found on page 51 of the log tables. These equations need to be changed for projectiles across a horizontal plane. As seen in the last part, U stands for initial velocity, V stands for final velocity, and S stands for distance, and here it is the same. The subscripts X and Y indicate axes. In this problem, the Y-axis is how high an object is going, while the X-axis is the range. Let's start with how we get these new equations. First, Ux and Uy are the I and j components, which are the names we give for the axes in applied maths. I equals the x-axis and j equals the y-axis. They are used to show the speed of an object in a given direction, or the velocity. The I is equal to ux, which is horizontal speed, and j is equal to uy, which is the vertical speed. Next is Vx. We derive this from the equation V equals u plus at. But in this problem, Vx is a constant as it is travelling horizontally, which means no other force affects it, and so the acceleration is equal to 0. This means Vx is the same as ux. On the other hand, Vy is affected by gravity due to it going upwards, and thus its equation is Vy equals uy minus gt. Sx and sy work under the same conditions, but instead are derived from s equals ut plus half at squared. These equations are Sx equals uxt and Sy equals uyt minus half gt squared. In these equations, we replace a, the acceleration, with g, the acceleration due to gravity. Let's move on to starting the equation by ways of finding ux and uy. As shown in the example, it is straightforward. The I component equals ux and the j component equals ui. But problems may arise when a certain velocity is given. This can be proven quite simply by using sine and cos. We know that the projectile is fired at a certain angle called theta, the weird looking circly thing. We can use this to find an expression for the I and j components. We make a right angle triangle with axes and use Pythagoras' theorem. Since we know the I component is equal to the velocity on the x-axis, this makes it the adjacent of our triangle, as it is parallel to the x-axis. This is the same with the opposite and y-axis. Important notice: if no velocity is given, we say the velocity is equal to u and use the same method here. Now, let's use these equations of ours to find the way in which we can find the max height and distance travelled by the projectile. We know certain rules about an object at max height. When at max height, its vertical component is 0. We first find the time, or t, when Vy equals 0. We then substitute this time value into Sy, and we get the max height. The range follows a similar method. We know that a projectile is on the ground at two moments, at the start before it is launched, and at the end when it hits the ground again. We can find the range by setting Sy equal to 0 to find the time, and then subbing this time value into Sx. Using the method of finding the range just explained, we can find the height of an object at a certain distance. This can be done by setting Sx equal to the desired distance, and then finding the time, and then subbing this value into Sy. This idea can be flipped to work out the distance at which the object has reached a certain height, by setting Sy equal to the desired height and subbing the time value into Sx. Last but not least is the way of figuring out the velocity at a certain point. First, you need to find out what Vx and Vy are. We already know that Vx is equal to ux, and you can obtain Vy by finding the time it has taken to reach a point and then subbing it in. Now, where do we go from here? Well, remember from a while back when we talked about the I and j components? Let's bring them back in. Since we know ux equals I and uy equals j respectively, we also know the I component equals the adjacent, while the j component equals the opposite. From there, we can find the magnitude, which is the hypotenuse, by using Pythagoras' theorem. Well, that's the end of the maths. Hope that helped and hope you understood. Enjoy the rest of the video. That's it. Please stick around for the credits.